It's David Spears, Civil Engineering Instructor at Texas Tech, talking about solids, CE 3303 class. We're in Chapter 13.3, really the first three sections of Chapter 13, talking about column design, in which we've talked about the development of Euler's load, the critical buckling load, and we've talked about different support conditions as they affect the slenderness ratio of the KL over R, or the effective length factor K. So this problem is a good example of that. I have a column in the given, and it's 5 meters tall, and at the top, at the base it's fixed, but at the top it's supported by a cable here in the X direction that it braces the column against any displacement in that X direction, but it does not restrain against displacement in the Y direction perpendicular to that. So I'll talk about that in a second. Here I'm given that Young's modulus is 60 gigapascals, the yield stress is 215 megapascals, the area is 0.0075 meters squared, its moment of inertia in the X direction about the X-axis is 61.3, 10 to the minus 6th meters to the 4th. Its moment of inertia in the Y direction, or about the Y-axis, is 23.2. The Y-axis is what we call the weak axis, and the X-axis is the strong axis. Okay, we've got to analyze, there's two different buckling conditions. One is in the X direction where it's braced or bending or buckling about the Y-axis. In that direction, the supports at the top are like this over here. They're pinned at the top and fixed at the bottom. Therefore, the effective length factor K is equal to 0.7. So KL is 0.7 times its length, or 5. So its effective length is 3.5 meters. Now Euler's equation is this 1 pi squared EI over KL squared. I plug in the knowns with this for E and this for IY, because it's the axis about which it's buckling. 3.5 is the effective length squared. I get 1308 kilonewtons is the Euler's load, the critical buckling load. Okay, the other condition is for buckling about the Y-axis, the X-axis, or in the Y direction. So that would be buckling this way, in which there's really no restraint at the top. So the supports are considered to be free at the top and fixed at the bottom. Just like this diagram shows, my effective length is twice my length, actual length. K is equal to 2.0. KL is 2 times 5, or 10 meters. I plug into the similar Euler's load equation. This time IX is what's in the numerator, and KL, the effective length, is 10. Square that, evaluate that, I get 423.5 kilonewtons. The smaller buckling load is the one that controls, because that's the one that's going to happen first, and so that's the buckling load for this condition, the maximum. The example 13.3 in the book applies a safety factor and figures out some the stress, but we're not going to bother with that right now for this example. Just divide that load by the safety factor, whatever it is, and then take P over A to figure out the axial stress, and you can finish that up